Soft drinks are a billion-dollar blend of chemistry, flavor, and fizz that captivate the world. From Pepsi's bold cola formula to Fanta's fruity burst and Dr. Pepper's mysterious 23 flavor mix, each soda is a masterpiece of carbonation and taste engineering. Today, we dive inside their bottling plants to see how these legendary drinks are brewed, blended, and bottled for that unmistakable pop. Pepsi begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5-to-1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens, and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces, syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drink's base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high-pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer, calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. The process for M&Ms begins with the preparation of the chocolate centers. For classic milk chocolate M&Ms, this involves creating a standardized chocolate blend using a combination of cocoa liquor, cocoa butter, milk solids, sugar, and lecithin. These ingredients are carefully measured and introduced into large industrial mixing vats. The ratio of milk solids to cocoa and sugar is adjusted based on the exact product line, whether it's milk chocolate, peanut, crispy, or almond. Once blended, the mixture moves to a refining stage, typically using a 5-roll refiner. This machine grinds the chocolate particles to an optimal size, usually under 25 microns, to ensure a smooth texture without any detectable grittiness. Following refining, the chocolate mass is transferred into conche machines, where it is continuously mixed and aerated under controlled heat. This critical step, often lasting up to several hours, develops the final flavor by driving off acidic compounds and ensuring that all ingredients are evenly emulsified. After conching, the chocolate is cooled and pumped into a tempering machine. Here, the chocolate is brought through a series of controlled heating and cooling stages to encourage the formation of stable cocoa butter crystals. This tempering process is essential for the final snap and sheen of the chocolate. Tempered chocolate is held in insulated storage tanks, stirred continuously to maintain consistency and prevent premature crystallization. To form the centers of M&Ms, the tempered chocolate is deposited into spinning molding drums, where small, consistent droplets are rapidly cooled to form uniformly sized spheres. In the case of peanut or almond M&Ms, the center process is different. Whole nuts are cleaned, dry roasted to exact specifications, and then tumbled in pans where successive layers of tempered chocolate are applied. Each pass adds a thin layer, and between coatings, the centers are cooled and stabilized to maintain roundness and uniform chocolate coverage. Once the chocolate cores, whether solid chocolate or chocolate-covered nuts, are ready, they are transferred to the panning room for sugar shell application. This is one of the most technically demanding parts of the process. The cores are loaded into large rotating pans, or dragee pans, that slowly tumble the centers while a thin sugar solution is sprayed onto them. As the pans rotate, the solution spreads evenly, and heated, dehumidified air is blown into the pans to evaporate moisture and crystallize the sugar coating. This process is repeated dozens of times. Each cycle deposits a very thin layer of sugar, which is dried and hardened before the next layer is applied. Through this repeated layering, the sugar shell grows gradually until the desired thickness is achieved. The conditions in the panning room are carefully controlled, with temperature, humidity, and airflow all precisely calibrated to prevent cracking, clumping, or uneven coatings. As the shelling nears completion, food-grade dyes are added to create the iconic M&M's color palette. Color application is done by loading batches into separate pans for each color. Liquid or powdered food coloring is sprayed or dusted over the still rotating candies, then sealed with a final transparent sugar polish. This step not only gives the candies their vibrant hues, but also produces the glossy finish M&Ms are known for. Modern facilities use optical scanners and machine learning algorithms to ensure each piece has uniform color coverage and no significant defects. Once the candy shells are colored and polished, the next step is the addition of the iconic M stamp. This is performed by a specialized printer equipped with multiple high-speed stamping heads. The M&Ms are spread out on a flat, vibrating conveyor belt that orients the candies so they're properly positioned for printing. Each printer head rapidly applies a food-safe white vegetable ink in the form of the lowercase m. The process is fast enough to stamp tens of thousands of candies per minute while maintaining alignment and clarity. After stamping, the candies are funneled into stainless steel hoppers where they cool briefly and are gently tumbled to remove any residual static electricity or misalignment. The candies then flow into the packaging line, which is equally sophisticated. M&Ms are portioned using multi-head combination weighers that ensure each packet receives an accurate fill weight. These weighers use vibrating chutes and load cells to dispense candies into forming machines that create the signature M&M's pouches or tubes from printed film. The packaging film is pulled, cut, and sealed around the candies in a vertical form-fill seal machine. Each pack is marked with a lot number, expiration date, and manufacturing code. Metal detectors and X-ray systems scan every packet for potential contaminants or packaging defects, and inline check weighers verify that the fill weight meets specifications. Any defective packs are ejected from the line automatically. Packaged M&Ms are then collected into cartons, which are barcoded and shrink-wrapped for shipping. These cartons are palletized by robotic arms and moved to climate-controlled warehouses. The temperature and humidity of these storage facilities are tightly controlled to prevent chocolate bloom or sugar shell degradation. The final step is distribution, with pallets sent out through a carefully coordinated logistics network to grocery stores, vending machines, and distributors around the world. Throughout the entire M&M's manufacturing process, quality control is constant. Samples are pulled at every major stage: chocolate refining, shell coating, coloring, stamping, and packaging. Technicians perform tests on texture, shell thickness, moisture levels, and color uniformity. Tasting panels sample daily to assess flavor, and sensory booths are used to eliminate bias during evaluations. Environmental considerations are also built into the process. Dust collection systems are used in sugar handling areas to minimize air particulates, and water used in cleaning is recycled where possible using filtration and sterilization. Temperature recovery systems reuse heat generated by panning dryers and conching machines, feeding it into the plant's HVAC system or hot water circuits. In modern M&M's facilities, much of this process is overseen by a central digital control room. Here, operators monitor flow rates, temperature curves, humidity levels, and output speeds in real time across multiple screens. Any deviation from target specifications triggers alerts, enabling rapid correction before quality is compromised. Machine learning algorithms analyze production data to forecast maintenance needs, optimize energy consumption, and predict the impact of recipe tweaks. So, while a single M&M candy may seem simple, just a tiny bite of chocolate with a hard shell, it is in fact the result of a multi-stage, intricately controlled system designed for scale, precision, and repeatability. Each piece is the culmination of decades of engineering, from chocolate particle refinement and shell layering to robotic stamping and data-driven packaging. The result is a product that delivers the same color, crunch, and creamy center millions of times a day all over the world. Wafer production begins with the precise mixing of a liquid batter made from wheat flour, sugar, vegetable oils, leavening agents, salt, and water. This mixture is pumped into a pressurized holding tank, kept under constant agitation to maintain uniformity. From there, it flows into a series of wafer baking plates arranged on a rotary belt oven. Each set of plates clamps down, spreading the batter evenly across the mold surface as it rotates through a high-temperature tunnel oven. The baking process takes less than 2 minutes, during which the wafer sheets are cooked evenly on both sides to a crisp, golden consistency. Optical sensors mounted along the oven track monitor browning levels and moisture content in real time, adjusting heat distribution if necessary. The fully baked wafer sheets exit the oven onto cooling conveyors equipped with forced air fans. Rapid dry cooling is critical to avoid humidity absorption, which could lead to soggy or uneven wafers. Once cooled, the wafer sheets are transferred to a stacking unit where they are automatically aligned and fed into the layering system. This system applies a uniform layer of chocolate-based filling using a grooved roller that spreads the cream with millimeter precision. This filling consists of sugar, cocoa powder, non-hydrogenated fats, and finely ground reprocessed wafers, which are reincorporated into the cream to create a consistent texture and minimize waste. Another baked wafer sheet is pressed on top, forming the next layer. Most Kit Kat bars use 3 wafer layers and 2 cream layers in alternating sequence. The stacked wafer blocks pass under a compression roller to ensure uniform density and adhesion between layers. Immediately afterward, the layered wafer slabs are conveyed to the cutting station. High-speed rotary blades or ultrasonic knives slice the slab into individual fingers. Each cut must be surgically clean to preserve the structural integrity of the wafer and prevent crumbling or edge collapse. Blades are cleaned automatically between cycles to prevent buildup. Next, the naked fingers proceed to the enrobing line. These bare wafer pieces are gently placed onto stainless steel mesh conveyors and passed through a flow of tempered chocolate. The enrober coats each finger completely, sides, bottom, and top, with a thin, even layer of chocolate. To prevent excess chocolate from accumulating at the base, air knives blow from underneath the mesh to clear pooling, followed by a vibrating section that helps settle the coating and eliminate surface bubbles. Tempering of the enrobing chocolate is critical here. The chocolate must be heated, cooled, and reheated in a precise sequence to promote stable cocoa butter crystallization. This gives the final product its distinctive glossy finish and crisp snap. Chocolate that isn't properly tempered can appear dull, bloom with fat crystals, or become too soft at room temperature. Once coated, the fingers are passed through a cooling tunnel that gradually reduces the temperature from about 30 degrees Celsius down to 10 degrees Celsius. This controlled descent ensures the chocolate solidifies uniformly without contracting too quickly or developing cracks. Cooling typically takes around 5 to 7 minutes and is performed in multiple zones, each with its own humidity and temperature controls. Sensors inside the tunnel detect surface gloss and chocolate hardness using reflectometers and pressure probes. If any deviation is found, the product is automatically diverted for reprocessing. At this point, the bars are ready for the branding stage. For standard 4-finger Kit Kats, an embossing stamp may be used to imprint the brand name into the chocolate coating while it's still slightly soft, just before final hardening. The embossed chocolate then continues along the line to the packaging area. Bars are counted, aligned, and guided into flow wrappers. A single horizontal form-fill seal machine wraps each bar in a foil laminate film printed with branding, nutritional information, barcodes, and lot numbers. The film is heat sealed around the chocolate in less than half a second, forming a tight, protective package. Each wrapped bar is then weighed using an inline check weigher to ensure proper chocolate fill and detect any anomalies. If the bar is too light or heavy, or if the seal is not correctly formed, it is rejected and sent to a secondary inspection lane. Successful bars are collected into batches for secondary packaging. This may include multi-packs, gift boxes, or variety bundles, depending on the product variant. Robotic arms arrange bars into trays or cartons, which are then sealed, labeled, and date-stamped by automatic systems. These boxes are stacked on pallets using robotic palletizers programmed with pattern optimization software to maximize space efficiency and ensure load stability. The completed pallets are shrink-wrapped and tagged with RFID identifiers that record batch data, origin, and destination logistics. Finished pallets are transferred to a temperature-controlled warehouse maintained between 16 degrees Celsius and 20 degrees Celsius with 45 to 55% humidity, ideal storage conditions to prevent chocolate bloom and preserve crunch in the wafers. All stages of production are monitored via a centralized manufacturing execution system, which links real-time sensor data, production schedules, and quality control checkpoints. Operators monitor dashboards that display belt speeds, oven temperature graphs, chocolate viscosity readings, packaging line uptime, and rejection rates. Every wafer, batch of chocolate, and final bar is fully traceable from ingredient origin to final pack, enabling precise recall or investigation in the rare case of a defect. Clean-in-place systems are integrated into most parts of the equipment, allowing the factory to perform daily automated cleaning cycles without disassembling major machinery. Water and detergent are flushed through piping, tanks, and depositor heads, followed by steam sterilization and final air purging. Swab tests and microbial sampling are done routinely, especially after allergen changeovers, such as moving between milk and dark chocolate lines or introducing limited edition flavors. The process of making Kit Kat bars, though outwardly simple in concept, wafers layered with cream and enrobed in chocolate, is actually one of finely balanced engineering. The crunch of the wafer, the creamy consistency of the filling, the uniformity of the chocolate coating, and even the tension of the foil wrap all contribute to a product that is as much about texture and satisfaction as it is about taste. Every part of the factory, from mixing vats to wrapping stations, operates in harmony to produce millions of identical bars that deliver the same experience each time. But Snickers' manufacturing process is even more impressive. Whole roasted peanuts arrive at the factory in bulk shipments and are immediately transferred into stainless steel holding silos equipped with air filtration and pneumatic transport systems. Before they're used, the peanuts are screened, sampled, and scanned for foreign materials using advanced sorting lines that include vibration screens, metal detectors, and high-speed optical sorters. Any discolored, shriveled, or malformed nuts are rejected. The selected peanuts are conveyed to large rotary roasters, where they are slowly tumbled in hot air at around 160 to 180 degrees Celsius. This roasting stage is critical, not only for flavor, but for ensuring that the final texture of the peanuts remains crunchy after they're embedded in caramel. Once the roasting cycle is complete, the peanuts are cooled rapidly using forced air systems to halt the cooking process and stabilize their structure. While the peanuts are being prepped, the caramel layer is produced in parallel. Granulated sugar, glucose syrup, sweetened condensed milk, and a blend of fats are mixed in steam-jacketed kettles with constant agitation. The mixture is heated to between 115 and 125 degrees Celsius, which caramelizes the sugars and thickens the mass. The cooking time and temperature are tightly controlled to achieve the exact stretchiness and chew required. Too soft, and it won't hold its shape in the bar. Too hard, and it becomes brittle. As the caramel nears its final temperature, milk proteins begin to break down, giving the mixture its signature golden color and deep, buttery flavor. Once ready, the caramel is pumped through heated pipes to a depositor, where it will be applied in a uniform sheet. The nougat layer, found beneath the caramel and peanuts, is created on a separate line. This begins with whipping a blend of sugar, glucose syrup, dried egg whites or hydrolyzed proteins, and milk solids in large planetary mixers. Nitrogen gas is injected during this mixing process to aerate the nougat, creating its signature light and chewy consistency. This mixture is then folded with a chocolate paste made from cocoa powder and oils to give Snickers nougat its slightly chocolatey tone. Once fully mixed, the nougat is extruded through wide slits onto a continuously moving belt to form a long, flat sheet that cools as it travels down the line. The caramel is poured directly onto the cooled nougat slab as it moves along the conveyor, forming the second distinct layer. Immediately after, the roasted peanuts are evenly scattered onto the still warm caramel using a vibratory spreader, ensuring every inch of the bar's width receives a consistent peanut distribution. Timing here is crucial. The caramel must be warm enough for the peanuts to adhere properly, but not so hot that they sink in or shift. This three-layer sheet, nougat, caramel, and peanuts, is allowed to set slightly before it moves into the slabbing station. Here, precision blades cut the wide slab into long, narrow ribbons. These ribbons are then rotated 90 degrees and fed into guillotine-style cutters that chop them into bar-length pieces. Each bar is now in its final shape, but still lacks the chocolate coating that completes the Snickers experience. The uncoated bars are lined up and transferred to the enrobing system. As they move along the stainless steel mesh conveyor, they pass beneath a curtain of tempered milk chocolate. This coating is supplied from a dedicated tempering machine that brings the chocolate through carefully managed heat cycles to promote the formation of stable cocoa butter crystals. The chocolate is heated to around 45 degrees Celsius to fully melt it, cooled to about 27 degrees Celsius to initiate crystal formation, and then gently reheated to 30 to 32 degrees Celsius to achieve the right viscosity and gloss. The bars pass under this curtain of chocolate, completely coating their tops and sides. Simultaneously, the conveyor dips the bars through a shallow reservoir of chocolate to coat their undersides. Immediately after enrobing, the bars are passed through a vibrating section and gentle air jets. The vibration removes any excess chocolate and smooths the surface, while the air jets help eliminate bubbles or irregularities. A final grooved roller may be used to apply a signature wave texture to the top of each bar before they enter the cooling tunnel. The cooling tunnel consists of a long, temperature-zoned chamber that gradually reduces the bar's internal and surface temperatures from the low 30s down to around 10 degrees Celsius. Cooling is done in stages to prevent thermal shock, which could cause chocolate to bloom or the caramel to separate. The humidity is also carefully controlled to prevent condensation or sugar crystallization. As the bars move through this tunnel over several minutes, the chocolate hardens into a stable, glossy shell that encases the caramel, peanuts, and nougat within. After cooling, the bars are discharged onto a secondary conveyor where they are spaced, aligned, and funneled into the wrapping line. Here, a horizontal form-fill seal machine envelops each bar in a printed plastic film that's been preloaded with branding, nutritional information, barcodes, and lot tracking data. The wrapping film is heat sealed around the bar and trimmed using rotary knives. Wrapping is synchronized precisely with the movement of each bar to prevent any misalignment or creases. After wrapping, the bars are scanned by metal detectors to ensure no metallic contamination has occurred during production. They're then passed through check weighers to confirm each bar falls within the designated weight tolerance. Any bar that falls outside these parameters is rejected automatically and sent to a collection point for analysis or recycling. Approved bars are sorted into cartons using robotic arms that can grip and group them based on SKU. These cartons are then sealed, coded, and stacked onto pallets using automated palletizers. Each pallet receives a printed label with batch information, destination codes, and compliance data. Before leaving the facility, all pallets are shrink-wrapped and staged in a temperature-controlled warehouse area where storage conditions are maintained between 16 and 20 degrees Celsius with less than 50% relative humidity. A centralized control room oversees all operations, using real-time data collected from each machine to ensure consistency and efficiency. Key metrics such as temperature curves, mixing durations, chocolate viscosity, output rates, and rejection levels are displayed on screens for operators and engineers to monitor. Any deviation outside acceptable tolerances triggers alerts and corrective actions, which are logged into the production management system for traceability. Production changeovers, such as switching between regular Snickers and Snickers almond or Snickers peanut butter, involve flushing the lines, sanitizing all contact surfaces, and performing allergen checks. Cleaning is often done with clean-in-place systems, which circulate heated detergents and rinse water through enclosed tanks, pipes, and pumps. Swab tests and visual inspections verify cleanliness before the next product is introduced. Throughout the process, quality assurance teams take samples at each stage, from nougat aeration to enrobing, for analysis. These samples are tested for moisture content, density, layer thickness, chocolate coating weight, and overall structure. Finished bars are also subjected to sensory testing by trained panels, who evaluate appearance, flavor balance, aroma, and mouthfeel. Sustainability measures are integrated into production as well. Heat generated from the roasters and tempering units is recaptured and used to pre-warm wash water or facility air. Water used for cleaning is filtered and reused in non-product contact systems. Packaging film is sourced from suppliers that meet recyclability and food safety standards, and efforts are ongoing to reduce the environmental footprint of the wrapping process. Every Snickers bar, while simple in form, is a result of hundreds of interlocked operations, each designed for speed, hygiene, consistency, and indulgent quality. The chewy nougat, stretchy caramel, roasted peanuts, and milk chocolate coating are all optimized for flavor release, structural contrast, and a repeatable experience in every bite. From roasting to wrapping, this process is replicated across multiple global production facilities, each maintaining the same high standards to deliver one of the world's best-selling candy bars. Reese's Peanut Butter Cups begin with the bulk delivery of raw peanuts to the factory's intake silos, where they are gravity-fed into the initial sorting system. These peanuts are inspected mechanically, using a combination of vibrating sieves and optical sorters to remove any debris, underdeveloped kernels, or foreign materials. Once sorted, the peanuts move via enclosed conveyors to massive gas-fired rotary roasters. These roasters tumble the peanuts at temperatures ranging from 160 to 180 degrees Celsius for up to 30 minutes, depending on the batch specifications. Uniform roasting is critical, as it directly impacts the flavor profile of the peanut butter core. Immediately after roasting, the peanuts are dropped into rapid cooling bins to halt the cooking process. Once cooled, they're transported to a dry de-skinning machine, where rubber-lined rollers strip the outer skins, which are then removed via airflow separators. The cleaned roasted peanuts are directed into hoppers that feed them into industrial grinders. The first stage produces a coarse paste, while the second stage refines this paste into a smooth, semi-solid mass with just enough texture to give Reese's its signature, slightly grainy peanut butter. At this stage, the peanut paste is blended with dextrose, salt, and a small quantity of vegetable oil stabilizers in jacketed mixing tanks. These tanks are equipped with high-torque agitators that ensure uniform mixing and prevent separation. The peanut butter is then pumped into storage tanks held at a steady 40 degrees Celsius to maintain pourability, with recirculation loops preventing oil separation. While the peanut butter is being prepared, the chocolate coating is simultaneously processed in a different section of the plant. Solid chocolate blocks arrive in insulated pallets and are broken down into manageable chunks by automated crushers. These chunks are melted in conical tempering kettles, where the chocolate is cycled through precise temperature phases. Heating to 45 degrees Celsius to dissolve fat crystals, cooling to 27 degrees Celsius to encourage type 5 crystal formation, and then reheating slightly to 30 to 31 degrees Celsius to prepare for molding. This tempered chocolate is fed through stainless steel piping with heated jackets into the deposition zone. The chocolate is deposited into paper-lined plastic molds using servo-controlled nozzles. The molds are pre-fitted with pleated paper cups, automatically dispensed and placed by robotic arms. The bottom layer of chocolate is dispensed in a circular motion to form a consistent base. The molds are gently vibrated on a plate to spread the chocolate evenly and eliminate air bubbles. Once the bottom shell is semi-set, the peanut butter is deposited in the center using another set of volumetric piston fillers. Each dollop is carefully controlled to ensure it stays centered and does not bleed into the side walls, which would prevent the top chocolate layer from sealing properly. The peanut butter is slightly cooler than the chocolate to preserve its form as it's deposited. The top chocolate layer is applied almost immediately after the peanut butter centers are deposited. Another set of nozzles applies tempered chocolate to fully enrobe the filling, again followed by brief vibration to ensure complete coverage and smooth surface finish. This layered structure of chocolate, peanut butter, and chocolate is the signature of every Reese's cup, and the volumes are calibrated down to the milliliter. Next, the filled molds enter a tiered cooling tunnel. This tunnel is divided into climate zones, with each zone dropping in temperature by small increments, from 20 degrees Celsius down to around 8 degrees Celsius, over the course of 15 to 18 minutes. This gradual cooling prevents thermal shock, which could cause cracking or separation between the chocolate and filling. Each zone is equipped with air circulation fans, refrigeration coils, and humidity control systems to ensure perfect crystallization of the chocolate. After the cooling process is complete, the now fully formed Reese's cups are ejected from their molds using a pneumatic plunger system that pushes from beneath the mold cavities. The cups remain in their paper liners and are transferred to conveyance lanes for wrapping. At this point, the cups are still exposed and vulnerable to environmental conditions, so the transfer occurs within a controlled, filtered air enclosure to prevent contamination. The wrapping process uses horizontal flow wrappers. Each Reese's cup is aligned via guide rails and funneled into individual wrapping lanes. Printed foil is unwound from rolls and cut to size by rotary knives. The cup is pushed onto the foil by a mechanical arm, and the foil is folded and sealed around the candy using heat-sealing jaws that close in fractions of a second. The wrapped cups are then printed with batch codes and expiration dates using inkjet or thermal printers. For king-size or multi-cup packages, the single wrapped cups are automatically grouped and loaded into larger overwrap film using a secondary wrapping machine. These packages are then loaded into display cartons by robotic pick-and-place arms that orient each unit for retail presentation. These cartons are glued or tab sealed, then labeled with product identifiers, shipping information, and QR codes for traceability. Before packaging is finalized, random samples are pulled from each production batch and sent to quality assurance labs. Here, technicians weigh each cup, examine chocolate gloss and thickness under calibrated lighting, and use penetrometers to test the firmness of the peanut butter. They also cut cross-sections of the cups to visually inspect layering uniformity and check for air gaps or structural flaws. Once cleared, finished cartons are palletized using robotic stacking systems that build stable load units based on truck optimization software. Each pallet is stretch wrapped and labeled with RFID tags that track its origin, contents, and destination. These pallets are loaded onto climate-controlled trucks that maintain the cargo area between 10 degrees Celsius and 22 degrees Celsius, preventing chocolate bloom or melting during transport. Even after the cups leave the factory, Hershey maintains control over their handling through advanced logistics software. This platform integrates sales forecasts, retailer data, and shipping conditions to prioritize inventory rotation and ensure that product closest to expiration is delivered first. Warehouses use automated pick systems and real-time barcode scanning to manage stock. In addition to the standard production line, seasonal Reese's cups, like pumpkin or heart shapes, are produced using interchangeable mold plates. These specialty shapes require adjustments in chocolate and filling deposition to accommodate varied volume and geometry. The same precision is applied to these runs, though the visual inspection is even more rigorous due to complex shapes. Flavor innovation is handled through a separate R&D pipeline. Variants like white chocolate or dark chocolate cups require their own tempering parameters and material handling systems to prevent cross-contamination. These are produced in small trial batches on modular production lines until formulations are approved for full-scale production. From a sustainability perspective, Hershey continuously works to reduce energy and material waste. Chocolate tempering kettles use thermal recirculation systems to recover heat energy, while the roasting exhaust is captured and scrubbed for reuse in preheating systems. All peanut skins, chocolate trimmings, and off-spec cups are collected and either reprocessed or converted into animal feed and energy through biodigesters. This entire system, roasting, grinding, tempering, depositing, cooling, wrapping, inspecting and shipping, operates in a tightly synchronized loop, monitored by real-time factory control software. Supervisors can access dashboards showing throughput, downtime, temperature profiles, and ingredient usage. Alerts notify operators of any deviations from specification, and corrective actions are logged for traceability. Every Reese's cup, whether it's a classic 2-pack or a seasonal novelty, is the result of layered processes fine-tuned to deliver the exact same flavor and texture every time. From the precise ratio of peanut to salt, to the sheen on the chocolate, to the shape of the paper liner, all of it is the product of exacting industrial craftsmanship. Mars chocolate bar production starts with the arrival of key ingredients at the facility: raw cocoa mass, cocoa butter, sugar, skimmed milk powder, lactose, glucose syrup, and proteins used in the nougat layer. All ingredients are subject to strict quality control before entering the production line. Cocoa mass and butter are delivered in solid block form, stored in climate-controlled zones, and tested for fat content, aroma, and particle size. Sugar arrives in bulk and is transferred pneumatically into silos. Milk powders are delivered in sealed containers, sampled for moisture and purity, then funneled to automated dosing stations. The chocolate phase begins with tempering and mixing. Cocoa mass and cocoa butter are first melted in stainless steel, jacketed tanks at precise temperature ranges, typically between 45 degrees Celsius to 50 degrees Celsius. This molten chocolate mixture is sent into high-capacity blenders, where sugar, milk powders, and lactose are added. The mixing process creates a coarse paste which then undergoes refining. Refining is done using 5-roll refiners, massive machines where the chocolate paste passes through a series of increasingly narrow steel rollers. These rollers compress the paste down to a fine particle size between 20 to 30 microns. This size range ensures that the final chocolate feels silky and not gritty. Sensors monitor the output continuously for particle size and adjust roller pressure accordingly. The refined paste is moved into conching machines, where it's heated and agitated for several hours. Conching removes volatile acids and moisture while developing flavor and viscosity. Emulsifiers like soy lecithin are added during this phase to control flow behavior. The conched chocolate is then pumped into holding tanks kept at 30 to 32 degrees Celsius, ready for use in bar coating and mold filling. In parallel, the nougat layer is being produced in a different section of the factory. Mars's nougat starts by mixing sugar, glucose syrup, and water in large cookers. This mixture is heated to form a syrup, which is transferred to industrial aerators. Here, whipped protein, often derived from egg whites or hydrolyzed soy protein, is added. The high-speed aerators incorporate air into the mix, giving nougat its light, chewy texture. Once whipped, the nougat is enriched with milk powder, fats, and flavoring components to build creaminess and mouthfeel. The warm, aerated nougat is extruded onto a continuously moving conveyor belt as a wide, flat slab. As it travels down the line, it is cooled by overhead airflow units to partially set its structure. Once firm enough, the nougat sheet is trimmed to a uniform width using high-speed rotary blades and moves to the caramel deposition stage. Mars caramel is produced using continuous vacuum cookers. Sugar, glucose syrup, and milk ingredients are heated under vacuum to lower the boiling point, preserving soft texture and rich dairy flavor. Once the caramel reaches the desired consistency, it is deposited as a thin, even layer over the traveling nougat base. This layered slab now resembles the cross-section of a Mars bar before chocolate coating. Cooling tunnels set the caramel onto the nougat layer using a staged drop in temperature from ambient to around 10 to 12 degrees Celsius. Once the slab is fully set, it moves to ultrasonic cutters. These high-frequency blades cut the slab into bar-length segments with minimal compression, maintaining clean edges and uniform size. Each bar now contains a core of structured nougat and a top layer of soft caramel, and is ready for chocolate coating. The next stop is the enrobing line. Each bar is placed onto a perforated conveyor belt and passes through a chocolate curtain, molten tempered chocolate falling in a continuous sheet. A bottoming roller ensures the underside is coated first. Air knives blow off excess chocolate and shape the final bar profile. Edge trimming guides ensure the sides are evenly coated without pooling. The entire chocolate coating process is conducted at controlled temperatures, usually around 30 degrees Celsius, to maintain chocolate viscosity and gloss. Once coated, the bars enter a long, refrigerated cooling tunnel. This tunnel gradually lowers the temperature over multiple zones, ensuring that the chocolate sets smoothly without cracks or bloom. Cooling takes roughly 12 to 15 minutes. Humidity is strictly controlled throughout to prevent condensation on the bars. Upon exiting the cooling tunnel, the bars are transferred to the wrapping station. Each bar is aligned into feeding lanes and enters a horizontal flow wrapper. Printed packaging film is unwound and formed around each bar. The wrapper is sealed using heat and pressure at the ends and along the back. Prior to sealing, the package interior may be flushed with nitrogen gas to remove oxygen and extend shelf life. Barcodes, batch codes, and expiry dates are printed in real time using high-speed inkjet printers. Cameras verify print legibility and seal integrity, and any faulty packages are ejected from the line. Accepted bars are automatically grouped into cartons, 12, 24, or 36 count configurations, depending on destination and retail requirements. Cartons are sealed with glue or interlocking flaps and labeled with destination codes. Palletizing robots stack cartons onto wooden or plastic pallets using algorithms that maximize load stability and cube efficiency. Once stacked, the pallets are stretch wrapped with plastic film and labeled with RFID tags containing tracking and batch data. These pallets are transported via forklifts or automated guided vehicles to temperature-controlled storage areas. Inventory management systems track product age and availability in real time. Orders are picked and dispatched using a just-in-time system integrated with retailer demand signals and distribution schedules. In addition to core Mars bars, the same line can be configured to produce variations such as fun size, twin pack, or regional editions. Changeovers involve switching cutting equipment, recalibrating depositor heads, and swapping packaging materials. This flexibility allows Mars to meet seasonal demand spikes or promotional formats without building entirely new production lines. Throughout the process, dozens of sensors, cameras, and feedback systems maintain quality. Chocolate viscosity is tracked with inline viscometers. Weight checks are performed on each bar using precision scales. And metal detectors ensure product safety. Quality control technicians also pull random samples hourly to inspect cross-sections, flavor, and mouthfeel. Sensory testing panels taste test bars daily to ensure consistency. Waste is minimized through rework systems. Off-spec nougat and caramel are reprocessed when possible, and chocolate trimmings are collected and remelted for future batches. Scraps unsuitable for reuse are converted to animal feed or processed through waste-to-energy systems. Sustainability initiatives have also taken hold. Mars uses responsibly sourced cocoa certified by third-party organizations and invests in water reduction systems and energy recovery technology in its factories. Packaging material is being reformulated for recyclability and reduced plastic usage. Each Mars bar, though it appears simple, is the product of a deeply engineered process, combining food chemistry, automated manufacturing, and strict quality assurance to ensure uniformity on a scale of millions of units per day. From raw cocoa mass to wrapped bar, the journey is a marvel of food industry precision. Snickers bars begin their life in a highly coordinated manufacturing facility where precision equipment, food science, and industrial engineering merge to produce one of the world's most popular candy bars. The process starts at the very foundation, the peanuts. Whole, raw peanuts arrive at the factory in food-grade bulk containers or via pneumatic tankers. These nuts are funneled into intake hoppers equipped with vibrating screens and magnets to remove stones, shells, or metal fragments. From there, they're transferred to silos with humidity and temperature controls, where they await roasting. The roasting process is crucial in developing the Snickers bar's signature crunch and roasted aroma. The peanuts are moved from silos into rotary drum roasters, which tumble them continuously at temperatures between 160 to 180 degrees Celsius. The roasting cycle is tightly timed, usually around 20 to 25 minutes, and computer systems monitor kernel temperature, moisture release, and color development using near-infrared sensors. Once roasting is complete, the peanuts are transferred to a cooling conveyor where chilled, filtered air rapidly reduces the kernel temperature, halting the cooking process and preserving the ideal crunch. After cooling, the peanuts are split into two processing streams. A portion is designated for whole peanut inclusion. These go through size grading systems and optical sorters that scan for broken or discolored nuts. Defective peanuts are automatically removed with precise puffs of air. The selected whole peanuts are sent to temporary storage hoppers until they are needed at the assembly stage. The other stream is milled into granulated peanut fragments. The peanuts pass through precision grinders that can be adjusted to produce different textures, from coarse granules to fine peanut meal. These different textures are essential as the coarse fragments are used in the caramel mixture for crunch, while the finer ones enhance the nutty flavor in the nougat. While the peanuts are being processed, the nougat, a critical layer in every Snickers bar, is produced in an adjacent line. The nougat base is made by mixing glucose syrup, sugar, powdered milk, and a whipped protein source, typically egg whites or hydrolyzed soy protein, isolate. These ingredients are heated in a batch cooker where sugar and glucose syrup dissolve and are cooked to a specific temperature to ensure the right consistency. The hot syrup is pumped into an aeration chamber where it's rapidly whipped to incorporate microbubbles of air, turning the dense syrup into a light, chewy base. To this base, ground peanut meal and sometimes cocoa powder are added, depending on the variation of Snickers being produced. The aerated nougat mixture is deposited onto a moving steel conveyor belt in a uniform slab, usually about 10 to 15 millimeters thick. The slab is leveled with motorized spreaders to ensure consistency in thickness, and then it enters a cooling tunnel. The tunnel gradually brings down the temperature of the nougat slab using fans and chilled air, solidifying the structure just enough for it to carry additional layers without collapsing. The next step is caramel preparation. Caramel for Snickers is not a generic mixture. It's custom designed for the brand's chewy, stretchy mouthfeel. It begins with a combination of glucose syrup, sugar, milk solids, and butter, cooked under vacuum to reduce the boiling point and develop flavor while maintaining softness. This caramel is cooked in large, continuous cookers that can process hundreds of liters per hour. The caramel is cooled slightly and mixed with coarse ground peanuts, creating the crunchy, rich upper layer of the bar. This hot caramel peanut mixture is deposited directly onto the cooled nougat slab. The deposition system includes a manifold that spreads the mixture evenly across the slab, forming a second layer. This dual-layered slab continues down the production line into another cooling tunnel, where the caramel firms up without hardening completely, remaining flexible for cutting. Once sufficiently cooled, the dual-layer slab is transported to the guillotine cutter. Using ultrasonic or hot wire blades, the slab is cut into bar-width strips and then into individual bar lengths, usually 50 to 60 grams each. These bars are then conveyed into the enrobing line, where they receive their final layer, chocolate. The chocolate coating used on Snickers bars is made in-house, using a proprietary blend of cocoa mass, cocoa butter, sugar, and milk powders. These ingredients are refined and conched in large machines that heat, mix, and aerate the chocolate to develop flavor and reduce particle size. The finished chocolate is held in jacketed tanks at a precisely controlled temperature of 30 to 32 degrees Celsius, ready for tempering. Tempering involves carefully controlling the crystallization of cocoa butter to ensure that the final chocolate has the right snap, gloss, and shelf stability. The tempered chocolate is pumped into enrobing machines, long tunnels, where a curtain of liquid chocolate coats the bars as they move along a mesh conveyor. A bottoming wheel applies chocolate to the underside of each bar, ensuring full coverage. Excess chocolate is removed using air knives, and the bars are passed under vibrating plates to level the coating. The coated bars are conveyed into a cooling tunnel approximately 20 to 30 meters long. The temperature in the tunnel drops from room temperature to about 8 to 10 degrees Celsius in graduated steps. This controlled cooling sets the chocolate without causing bloom or shrinkage. By the time the bars emerge, they are fully formed and ready for packaging. Each Snickers bar is picked up by robotic arms and placed into horizontal flow wrapping machines. Printed packaging film is formed around the bar, sealed at both ends and along the back using heat sealing jaws. The sealed bars are printed with a batch number, expiry date, and traceability code. Optical scanners inspect each package for proper seal integrity, print clarity, and alignment. The wrapped bars are grouped into cartons using high-speed collation systems. Depending on the SKU, bars may be packed into boxes of 12, 24, or 48 units. The cartons are sealed, labeled with logistics and traceability data, and palletized by robotic stacking systems. Pallets are shrink-wrapped and moved to staging areas for shipment. Throughout this entire process, quality assurance plays a vital role. Inline sensors and cameras continuously monitor chocolate viscosity, nougat density, caramel flow rate, peanut distribution, and packaging integrity. Manual samples are taken hourly and cut open for cross-sectional inspection. Taste tests are conducted daily by trained sensory teams who evaluate aroma, flavor, mouthfeel, and visual quality. Products that fail any stage of inspection are diverted, documented, and analysed to prevent recurrence. Snickers factories are designed with food safety and hygiene as top priorities. Staff wear full PPE, including hairnets, gloves, and smocks. Entry to production areas requires hand washing, sanitization, and often passing through air showers or floor sanitizers. All surfaces are made of food-grade stainless steel, and machinery is built with clean-in-place systems that allow automated washing and sanitization between batches. Environmental sustainability is another integral part of Snickers manufacturing. Mars, the parent company, implements energy-efficient roasting systems that recover heat, water reclamation systems that treat and reuse rinse water, and LED lighting to cut emissions. Chocolate and nougat trimmings are collected and either reused in new batches or converted into animal feed, while packaging material waste is recycled or reused wherever possible. From the first roasted peanut to the moment the wrapper is sealed, the making of a Snickers bar involves over a dozen steps, hundreds of parameters, and thousands of quality checks. Every component, from the protein foam in the nougat to the precise shear profile of the caramel, the fat crystal structure of the chocolate, and the crunch of the peanuts, has been engineered and tested to deliver a consistent, craveable bite. This integration of traditional confectionery with high-efficiency industrial production is what enables Snickers to be produced in the millions each day, while maintaining the same rich, multi-layered flavor and texture that has made it a global staple for decades. The manufacturing journey of Doritos begins long before the chips ever hit the fryer or the seasoning drums. It starts in the cornfields. Doritos use a specific variety of whole kernel yellow corn selected for its starch content, moisture levels, and particle uniformity after grinding. The corn is harvested at peak maturity and tested for aflatoxins, foreign material, and protein content before it's even accepted at the plant. Only corn that passes this first round of quality standards is brought in for processing. At the factory, truckloads of bulk corn arrive daily and are funneled into underground receiving pits that use gravity to guide the kernels onto conveyor belts. These conveyors feed the kernels into the first stage of preparation, the cleaning and sorting system. In this system, the corn passes through an array of vibrating sieves, rotating drum sifters, and powerful pneumatic air classifiers. Large debris like cobs, sticks, or stones are removed first. Then, finer contaminants like dust and small broken kernels are extracted using aspirators that draw away lightweight particles. Magnetized rollers also scan the corn flow to remove any traces of ferrous metal, ensuring total cleanliness before cooking. Once cleaned, the corn moves into the nixtamalization phase, a crucial and traditional process that transforms the flavor, texture, and nutritional properties of the corn. Nixtamalization involves cooking the whole kernels in a large stainless steel vat of hot water mixed with food-grade calcium hydroxide, also known as slaked lime. The corn is cooked at around 85 to 90 degrees Celsius for approximately 20 to 40 minutes, depending on the batch size and corn variety. This lime water solution serves several purposes. It breaks down the outer pericarp of the kernel, making it easier to grind and digest. It also increases the bioavailability of niacin, softens the internal structure of the corn, and imparts the distinctive flavor profile that Doritos are known for. After cooking, the corn is not immediately processed but left to soak, usually for 8 to 12 hours in the same solution. This extended soaking allows the lime to fully penetrate the kernel and continues the softening and flavor-enhancing process. After the soaking phase, the corn is drained and rinsed thoroughly in large industrial washers that spray it with jets of clean water while gently tumbling the kernels. The goal is to remove the loosened pericarp, excess lime, and any residual cooking liquid. What remains is called nixtamal, a soft, pliable corn mass that still holds the shape of whole kernels, but has a meaty, hydrated texture. The nixtamal is now ready to be ground into masa, the dough-like base of every Dorito chip. The grinding is performed using industrial stone mills, rotating horizontal stones made of volcanic rock or synthetic composites, precisely aligned to maintain a consistent grind size. The nixtamal is fed between the stones, and the pressure shears the softened corn into a dense, cohesive paste. This paste is the masa, and its texture is critical. It needs to be soft enough to press, but dry enough to hold shape without sticking. Operators continuously monitor the temperature of the mesa during grinding. Too much friction can overheat the dough, which affects the final chip texture. Ideal mesa temperature coming off the stones is around 45 to 55 degrees Celsius. Viscosity is checked using inline sensors that measure flow resistance, and if adjustments are needed, small amounts of water or returned dry mesa are mixed back in using an automated feedback loop. Now, it's time to form the masa into flat sheets. The ground mesa is transported via auger screws into a sheeting machine, which extrudes the dough between two polished stainless steel rollers. These rollers are adjustable to control sheet thickness down to the millimeter, usually targeting between 1.2 and 1.8 mm, depending on the final chip specification. The mesa sheets are laid directly onto a continuously moving conveyor belt that carries them to the cutting station. The cutting system is a rotary die cutter, a high-speed drum outfitted with rows of equidistant triangular blades, each perfectly matched to the iconic Doritos shape. As the mesa sheet moves beneath the drum, the rotating blades stamp out thousands of identical triangle chips per minute. Each cut is sharp and precise, with just enough spacing to leave minimal waste dough between cuts. The trimmings, the thin slivers of masa between triangles, are not discarded. They are automatically lifted via vacuum collection and returned to the start of the sheeting process. These scraps are reincorporated into the fresh dough, ensuring efficient use of material and maintaining consistency. The cut triangle chips now move on a flat conveyor to a brief baking phase, which we'll explore in detail in the next section. This preliminary baking is vital to reduce moisture and stabilize the chip before it enters the high heat frying zone. But before any oil is introduced or seasonings are applied, this early stage, cleaning, nixtamalization, grinding, sheeting, and cutting, is where the foundation of Doritos' crunch, shape, and flavor truly begins. Once the precisely cut mesa triangles are formed and conveyed forward, they reach one of the most critical transitions in the Doritos factory, the pre-baking zone. Though often overlooked, this short but essential phase serves as a structural stabilizer that prepares each chip for frying without deforming, bubbling uncontrollably, or becoming overly saturated with oil. This stage controls the internal moisture content and builds the texture foundation that will result in the signature crunch. The masa triangles, still soft and slightly tacky from the sheeting process, move onto a continuous metal mesh conveyor belt that leads directly into an industrial tunnel oven. This pre-bake oven is not designed to fully cook or brown the chip. Instead, its primary goal is to reduce the moisture level from roughly 50% down to about 25 to 30%. This ensures the surface of the chip becomes firm enough to hold its shape when exposed to hot oil, but not so dry that it resists expansion. The oven itself is typically divided into multiple thermal zones. The first zone begins around 160 degrees Celsius, gradually increasing to about 260 degrees Celsius by the final section. Heated air is circulated by high-velocity blowers, creating a turbulent flow across the top and bottom of the chips to ensure uniform dehydration. The baking conveyor is made of stainless steel mesh that allows hot air to penetrate from below, guaranteeing that no side of the chip is undercooked. Sensors monitor humidity at various checkpoints, and real-time data is fed into the oven's PLC system to dynamically adjust airspeed and temperature depending on fluctuations in mesa density, ambient humidity, or line speed. As the chips exit the oven, they emerge firmer, drier, and more resilient, yet still pale in color and lacking the blistered surface texture that defines a finished Dorito. That transformation happens in the next stage, the continuous fryer system. Here, the par-baked chips fall gently off the oven belt and descend onto the infeed section of a massive open-surface fryer. The fryer itself is a high-capacity stainless steel vessel filled with continuously filtered cooking oil. Most Doritos production lines use either corn oil, sunflower oil, or a proprietary blend of vegetable oils chosen for their high smoke points and neutral flavor profiles. The oil is maintained at a stable frying temperature of approximately 180 degrees Celsius, with variations of only +2 GC allowed during operation. Chips are submerged in the oil for about 35 to 55 seconds, depending on their exact moisture level and thickness. The chips ride through the fryer on a submersion conveyor, essentially a mesh belt with downward pressure bars that keep the chips fully immersed while preventing stacking or overlap. This is crucial because the frying process is not just about dehydration, it's about vaporization. As the residual water inside each chip turns to steam, it forces itself outward, puffing the chip slightly and creating those micro blisters and bubbly textures on the surface. This internal steam pressure is carefully managed. Too little and the chip stays flat and hard. Too much and it balloons into a hollow pocket. Above the fryer, exhaust hoods pull away steam and vaporized oil particles, filtering them through a heat recovery system that can reuse waste heat to pre-warm incoming oil. This system conserves energy and helps maintain a cleaner frying environment. The oil itself is constantly recirculated through centrifugal filters and fine mesh screens to remove crumbs, starch residues, or burnt particles. Fresh oil is added in controlled volumes throughout the day to maintain chemical balance and replenish lost volume. Once fried to the optimal light golden color, the chips are lifted from the oil by an outfeed conveyor and immediately pass through a vertical de-oiling section. Here, powerful centrifugal blowers aimed at precise angles blast away excess surface oil. This keeps the chips crispy, prevents pooling in the packaging stage, and ensures that the seasoning will stick without creating grease buildup. The chips then pass through an ambient cooling tunnel to bring them quickly down to room temperature. Cooling is not merely for worker safety, it stabilizes the fat within the chip and prevents condensation when entering the seasoning drums. Now comes one of the most defining stages of the entire process: seasoning application. Each Dorito must carry the bold, vibrant flavor profile it's known for, whether that's nacho cheese, Cool Ranch, spicy sweet chili, or any of the dozens of global variants. The seasoning powder itself is a proprietary blend of flavorings, including real cheese powders, spices, salt, sugar, yeast extract, and encapsulated flavor oils that deliver controlled release bursts of taste. The chips are conveyed into a rotating seasoning drum, an inclined, slowly turning cylinder lined with food-grade stainless steel. As the chips tumble over one another, a dry powder dosing system mounted above the drum applies the seasoning using precision augers and dispersing nozzles. These nozzles can spray a uniform mist of oil if needed before the seasoning hits, which enhances adhesion for certain formulations. The rotation speed of the drum, the flow rate of the powder, and the incline of the system are all adjustable and carefully tuned. Too slow, and the powder won't distribute evenly. Too fast, and the chips may break or the powder may collect unevenly on some sides. Optical sensors track the color and surface reflectivity of the chips as they exit the drum. If the reflectivity is too high, that could indicate under-seasoning. If it drops below a preset threshold, over-seasoning may be occurring. This live data is fed back into the controller, which tweaks the feed auger speed or pauses the oil spray accordingly. The seasoning drum is one of the most customized parts of the Doritos line. Different flavors use different particle sizes, densities, and oil volumes, which means the drum design and spray system must adapt depending on the product. Some drums include vibrating baffles or spiral lifts that increase tumbling action for extra thick chips or extra coarse seasoning. Once seasoned, the chips are directed into the weighing and bagging system, but before that, they undergo an automated inspection phase. High-speed vision cameras scan every chip for size, shape, and color. Broken chips, overly curled pieces, or visibly under-seasoned chips are removed via air-jet rejectors. These rejected chips are collected and sent either for regrinding or biomass energy use. Only chips that pass inspection enter the multi-head weighers, machines equipped with a dozen or more radial weighing hoppers. These hoppers constantly drop chips into a central collection bucket when the combined weight equals the target for each bag, typically between 28 g and 198 g, depending on package size. Once a precise combination is reached, the chips are dropped into a vertical form-fill-seal bagging machine. Here, continuous rolls of metallized polypropylene film are formed into tubes, sealed along the sides, and crimped at the bottom. The weighed chips are dropped into the formed bag tube just before the top is sealed and cut. Each bag is nitrogen flushed to displace oxygen, extending the product's shelf life and preserving crunch. Then, the bags are labeled, batch coded, and pass through a final metal detector before being boxed for palletization. After the freshly seasoned Doritos chips are individually weighed, bagged, sealed, and inspected, the production line moves into the critical post-packaging and logistics phase, where efficiency and traceability become as important as taste and texture. Though the chips are now fully formed and flavor complete, the operation is far from over. In fact, from a manufacturing systems perspective, the next stages, palletization, storage, shipping, and quality verification, are just as sophisticated and optimized as any in the earlier production line. The newly filled Doritos bags exit the form-fill-seal machines onto a series of conveyor belts designed to collect, orient, and organize them by SKU, bag size, and flavor variant. These conveyor lines merge into case packing stations, which use robotic arms equipped with vacuum suction grippers or gentle mechanical paddles to lift and place the chip bags into cardboard cartons. These boxes are pre-folded, glued, and printed with relevant product information, including product code, flavor, best before date, factory location, and a scannable QR or barcode that links to all production details. Each carton is inspected for weight and shape before it moves to the next phase. Even slight deviations in shape, caused by mispacked bags or an uneven number of chips, can disrupt downstream palletizing operations, so edge integrity and sealing quality are monitored automatically using high-resolution 3D scanning systems. Any carton that fails to meet dimensional tolerance is rejected from the main flow and rerouted for manual inspection or reboxing. Once cleared, the filled cartons are transferred to automated palletizing stations. In most modern Doritos factories, this process is entirely robotic. A multi-axis robotic arm lifts groups of cartons and stacks them onto wooden or composite pallets according to a predefined stacking pattern optimized for shipping efficiency and stability. These patterns are determined by a logistics algorithm that accounts for box dimensions, weight distribution, and the pallet's ultimate destination, whether that's a domestic warehouse or a long-haul overseas container. After each pallet is completed, A robotic stretch wrapper encircles it with several layers of clear plastic film to stabilize the load. A printed pallet ID label is affixed, containing detailed information about its contents, including product types, quantities, batch numbers, and destination. These labels are scanned into the warehouse management system, linking each pallet to the larger production database in real time. From here, pallets are routed into the warehouse zone. Doritos production facilities feature climate-controlled warehouses designed to maintain product quality throughout the storage period before distribution. These zones are not refrigerated, as Doritos are shelf-stable, but they are meticulously managed to avoid conditions that could lead to staleness or packaging deformation. Temperatures are generally held between 18-22 degrees Celsius, and humidity is controlled below 50% to prevent foil bags from absorbing moisture or warping. Inventory in the warehouse is managed by automated storage and retrieval systems. Tall racking structures are navigated by robotic cranes that pick and place pallets based on real-time demand, stock rotation policies, and shipping schedules. Each pallet's position in the warehouse is logged down to the specific shelf and column level, making retrieval highly efficient. The warehouse management system is integrated with the factory's enterprise resource planning software, ensuring that production and distribution are fully synchronized. While in storage, every pallet of Doritos is subject to randomized quality control sampling. A team of trained technicians removes sample bags from various pallets across shifts and production lines and sends them to a separate sensory evaluation lab within the facility. Here, samples undergo a series of tests: mechanical compression for bag integrity, gas analysis for nitrogen content, and oxygen intrusion, seasoning density checks, and most importantly, taste and crunch testing. Crunch is measured using a texture analyzer, a machine that applies controlled force to the chip and records resistance, fracture point, and acoustic feedback. The results are compared to golden standard reference chips to determine if the texture profile remains within acceptable limits. Seasoning adhesion and intensity are tested via flavor profile mapping, and every element from saltiness to umami to residual aftertaste is scored and compared against target values. If a trend of inconsistency is detected, an investigation is initiated, often leading to a review of upstream production parameters like fry temperature variability, seasoning drum throughput, or even ingredient batch variations. This closed-loop system helps prevent long-term quality drift and enables real-time course correction. Beyond the factory, the logistics infrastructure that gets Doritos from warehouse to retail shelves is another marvel of scale and precision. The factory works in tandem with PepsiCo's broader distribution network, which includes regional distribution centers, cross-dock terminals, and last-mile delivery nodes. Based on retail demand forecasts drawn from sales data, seasonal trends, and real-time POS metrics, shipment volumes are adjusted dynamically. This avoids overproduction and waste while ensuring retailers remain stocked. Each shipment of Doritos is accompanied by a digital bill of materials, which includes all traceability data from ingredient sourcing to packaging and palletization. This document allows not only for internal tracking, but also rapid action in the event of any product recall or customer complaint. If an issue is raised about a particular bag, say under-seasoning in a certain region, operators can trace the issue back to a specific lot, machine, shift, and even the original corn batch used in production. Globally, the manufacturing process for Doritos is also adapted based on regional consumer preferences and regulatory standards. While the foundational steps remain consistent: nixtamalization, sheeting, cutting, frying, and seasoning, the recipes and specifications can vary significantly. For example, in the US, cheese-based seasonings often use cheddar powder and lactic acid for tang, while in the UK or India, formulations may include less salt or alternative flavor enhancers to meet local guidelines or taste expectations. In markets like Japan or South Korea, where flavor sophistication and novelty are highly valued, factories produce limited edition Doritos featuring ingredients like wasabi, squid ink, or yuzu citrus. These variations often require changes in seasoning particle size, oil stability, or packaging material, and as such, the production lines must remain flexible. To facilitate this, Doritos factories use modular flavor dosing systems and quick changeover machines that allow seamless transitions between variants with minimal downtime. In addition to this flexibility, Doritos production lines are increasingly being outfitted with smart factory technologies. These include IoT sensors, predictive maintenance platforms, and AI-driven scheduling software. For instance, a vibration sensor might detect a subtle change in the seasoning drum's motor function that suggests a bearing is beginning to fail. Rather than waiting for a breakdown, the system automatically schedules maintenance during a planned production lull, avoiding unplanned downtime. Energy efficiency is also a growing focus. Waste heat from the fryers is often recovered through heat exchangers and used to preheat water for the nixtamalization tanks or warm the air in the seasoning room. Air filtration systems recycle hot air from the fryer exhaust into the building's HVAC to reduce natural gas usage. These sustainability practices help reduce both costs and environmental impact. Waste reduction is another area of innovation. Trimmings from mesa sheeting, broken chips, and seasoning dust are no longer treated as loss. Instead, they're collected, analyzed, and often reused in animal feed production, compost systems, or converted into biofuel at third-party processing facilities. Factory waste targets are set annually, and each production shift is scored on both yield efficiency and environmental impact. Ultimately, the journey of a Dorito from corn kernel to crunchy triangle is one of constant refinement. At every stage, whether it's dough hydration, fryer calibration, seasoning density, or robotic case packing, the process is governed by a matrix of mechanical precision and human sensory experience. The chips may seem simple to the average consumer, but behind every bag lies a production system that blends food science, industrial engineering, supply chain logistics, and consumer psychology into one unmistakable result: bold flavor, addictive crunch, and global brand consistency. It all starts with the consumer insight team, which continuously analyzes sales data, social media trends, cultural food movements, and even fine dining innovation to identify gaps or opportunities in the market. A spike in interest around birria tacos, for example, might inspire a spicy beef consommé Doritos concept. Once a viable trend is spotted, food scientists and flavor chemists work alongside marketing strategists to develop flavor direction briefs, detailed documents that outline the intended taste profile, emotional positioning, and target audience. In PepsiCo's Flavor Innovation Centers, teams begin with flavor mapping. This involves breaking down target flavors into their basic aromatic and taste components. For a concept like Flamin' Hot Dill Pickle, the scientists would analyze heat components, acidity, herbal notes, and salt balance. Using GCMS, flavor chemists extract and replicate aromatic profiles to ensure they match real-life foods as closely as possible. Next, benchtop seasoning blends are created in small batches using food-grade flavor powders, encapsulated oils, anti-caking agents, and natural extracts. These are applied to test chips using miniature tumblers that mimic the behavior of full-scale seasoning drums. Each test batch is evaluated by sensory panels, trained tasters who assess flavor intensity, balance, aftertaste, aroma, and how the flavor interacts with the chip's natural corn and oil base. Their feedback is mapped against a flavor wheel to identify gaps or off notes that require reformulation. Multiple iterations are often needed. Some spices may clump, certain acids might degrade in heat, And some flavor oils could lose their punch after just a few days in packaging. Stabilizers and carriers are used to protect volatile components, and microencapsulation techniques ensure that heat-sensitive ingredients only release during mastication, not while sitting in the bag. Once the flavor passes internal panels, the next phase is consumer testing. In select cities, Doritos organizes blind taste tests, sometimes with up to 500 participants per flavor. Reactions are scored not only on flavor, but on memorability, uniqueness, and potential repeat purchase behavior. Statistical modeling software crunches this data to identify the most promising formulas. When a flavor is approved, it must be scaled up to factory levels without losing its integrity. Seasoning blends are manufactured in industrial blenders, often in batches of hundreds of kilograms. The bulk seasoning is tested for particle size, uniformity, moisture absorption, and flow behavior. During this phase, the seasoning is often reformulated slightly for stability, color consistency, and performance under high-speed drum tumbling. Then come the pilot runs. A limited quantity of chips is produced on a full-scale Doritos line using the new flavor. This lets engineers monitor how the seasoning behaves under actual production conditions, how well it sticks to the chip, whether it builds up on machinery, how the oil in the powder affects packaging line sensors. If issues arise, tweaks are made not just to the formula, but to the machinery settings as well. Finally, once all checks are passed, the new flavor enters full production, often accompanied by bold marketing campaigns and timed releases. Global coordination ensures that ingredients meet regional compliance, and new flavors often debut in test markets before rolling out broadly. These launches are tracked in real time, and consumer response loops back into the development pipeline, influencing which flavors stay, evolve, or disappear. This highly coordinated, scientific, and iterative approach allows Doritos to launch daring new flavors while maintaining the consistency and production efficiency that a global brand demands. Each new taste starts with creativity, but ends in finely tuned, factory-scale execution. It all begins with the peanuts. While it might seem obvious that a peanut butter cup would start with peanuts, what's not widely known is just how much control and specificity Hershey applies to this ingredient before it ever reaches the cup itself. Reese's production lines require massive quantities of peanuts, hundreds of tons per week across facilities, and not just any peanut will do. The factory demands high oleic runner peanuts, most commonly sourced from farms in Georgia, Alabama, and Texas. These peanuts are preferred for their uniform kernel size, mild flavor, and high oil content, which delivers a creamier peanut butter base. Once harvested, peanuts are sent to dedicated shelling and blanching facilities, where they are cleaned, sorted, and skinned. The outer red skins are removed through dry abrasion, and the kernels are visually and electronically inspected to eliminate any with defects, mold, or foreign materials. Only the highest grade peanuts, typically designated as US Fancy or US Extra Large, are accepted for Reese's production. These peanuts are then loaded into food-grade hoppers and shipped in sealed bulk containers to the peanut butter manufacturing lines at Hershey's centralized processing plants. Upon arrival at the factory, the peanuts are stored in stainless steel silos within a climate-controlled environment to prevent spoilage. Prior to use, the peanuts are metered into roasting drums. Roasting is a critical step not just for flavor, but for aroma development and moisture reduction. High-capacity rotary roasters or continuous conveyor-style roasters are used, depending on the factory's line design. Peanuts are typically roasted at temperatures between 320 degrees Fahrenheit and 360 degrees Fahrenheit for 30 to 45 minutes. The exact temperature curve is adjusted based on peanut moisture and oil content, which is sampled batch by batch in the factory's lab using gas chromatography and moisture analyzers. The roasters are equipped with air impingement systems and inline sensors to monitor internal temperature, color, and roast development in real time. At various intervals, small test samples are pulled using auto draws for taste panel review. Roast level has to be absolutely consistent, as this is the foundation for the signature Reese's peanut butter flavor. Over-roasted peanuts will produce a burnt or overly bitter taste, while under-roasting leaves the flavor bland and oily. Once roasted, peanuts are cooled using high-powered air chillers to prevent overcooking and to stabilize the oils. They are then conveyed into degermers and mechanical splitters, where they are cracked open and the hearts, the hard inner core of the peanut, are removed. These hearts, while technically edible, can impart a bitter or chalky aftertaste, so they are separated out and typically used in livestock feed or secondary food processing streams. Now comes the grinding phase. The roasted and cooled peanuts are fed into large, high-shear grinders, industrial versions of what's used in commercial peanut butter production. These grinders operate at extremely high RPMs and are often configured in a two-stage system: a coarse grind followed by a fine grind. In the coarse phase, the peanuts are broken down into a grainy paste, preserving small particulates that contribute to the slightly gritty texture of Reese's peanut butter. This paste is then piped into a second mill, where it's refined to a smooth, uniform consistency. The peanut paste is blended in stainless steel mixing tanks equipped with variable speed paddles and heated jackets. At this stage, a proprietary mix of additional ingredients is incorporated. These include salt, sugar, a small amount of fully hydrogenated vegetable oil, and a dry milk derivative. The sugar used is finely milled and sieved to a consistent particle size, ensuring it disperses evenly throughout the mix without recrystallizing. Emulsifiers such as mono and diglycerides are added in microdoses, enabling the fat and protein phases to remain homogeneous over time. What makes Reese's filling unique, and one of the factory's guarded secrets, is its texture. It isn't traditional creamy peanut butter. It's dry and crumbly, almost fudge-like, but melts smoothly on the tongue. This is achieved by very specific moisture and fat content targets. The factory carefully controls the fat ratio in the peanut blend using inline nuclear magnetic resonance sensors, which measure fat levels without destroying samples. The ideal balance results in a pliable, moldable filling that holds its shape during chocolate enrobing but softens under bite pressure. Once blended, the peanut butter filling is pumped into chilled hoppers and held at precise temperature, typically between 60 degrees Fahrenheit and 70 degrees Fahrenheit, so it can be extruded or deposited with exact weight and shape control. Temperature consistency is crucial here. Too warm, and the filling becomes too soft and spreads when deposited. Too cold, and it hardens and resists clean shaping, risking damage to the chocolate cup. The final stage in this first segment is the formation of the peanut butter centers. On a separate production line, the cooled peanut filling is portioned using servo-driven pistons or extrusion rollers, depending on the cup format being produced. These machines deposit small, perfectly measured mounds of filling onto a chilled conveyor. In larger cups, the filling is puck-shaped. In minis, it's closer to a small dome. Each peanut butter deposit is then transferred into a temporary holding tunnel, essentially a refrigeration corridor, where the shaped fillings are stabilized prior to the chocolate enrobing phase. Here, humidity and temperature are carefully balanced to avoid condensation or fat bloom when chocolate is later applied. At this point, the peanut butter centers are firm, uniform in size and shape, and fully ready for the next critical phase of the process, chocolate molding. With the peanut butter centers now precisely formed, cooled, and stabilized, the next critical phase in the industrial production of Reese's peanut butter cups begins: chocolate shell creation and cup assembly. This portion of the process is all about precision, timing, and the seamless integration of multiple complex systems to produce a product that's visually perfect and texturally balanced. It's here that the familiar cup shape begins to take form, and where Hershey's decades of manufacturing expertise are on full display. The chocolate used in Reese's products is developed in-house and differs slightly from that used in a Hershey's milk chocolate bar. While it still contains cocoa solids, cocoa butter, milk solids, sugar, and lecithin, it has been tailored specifically to pair with the salty sweet peanut butter filling. The chocolate is slightly softer in melt, less bitter than dark chocolate, and has a fat and sugar profile that ensures it doesn't overpower the filling. It's formulated to be both moldable and stable under typical shelf conditions, even in warmer climates. The chocolate arrives at the cup production line in a liquid state, held in large tempering tanks kept at a precise temperature, usually around 30 to 32 degrees Celsius for milk chocolate. Tempering is an essential part of chocolate manufacturing and involves heating the chocolate to fully melt its cocoa butter crystals, cooling it to initiate the formation of stable type 5 crystals, then gently reheating it to bring it to working temperature. This process ensures that once the chocolate is set, it has a glossy finish, resists bloom, and has a clean snap when broken. The first step in forming the Reese's cup is lining the signature brown paper cup mold with chocolate. The production line is fed with pre-formed paper cups stored in large reels or stacked columns that are automatically dispensed onto a high-speed conveyor. These paper cups are food-grade, waxed, or coated with a thin moisture barrier and shaped precisely to hold their structure during and after chocolate deposition. Once the paper cups are set in place on the moving line, a chocolate depositor head releases a measured dose of tempered chocolate into each one. This is known as the bottoming phase. The amount of chocolate is critical, not only for structure, but also for controlling the ratio of chocolate to filling. After deposition, the cups pass over a vibration table. This stage is crucial for evenly spreading the chocolate along the bottom and slightly up the sides of the paper cup. The vibration table uses rapid, controlled pulses to remove air bubbles and to ensure a uniform shell that won't crack or collapse during filling. Immediately following the bottoming step, the peanut butter centers are dropped into the liquid chocolate. These centers have been transferred from the refrigerated holding tunnel to the enrobing line and are picked and placed with robotic arms or pneumatic suction systems that gently lower each piece into its corresponding chocolate-lined cup. The timing of this placement is perfectly synchronized so that the peanut butter slightly sinks into the chocolate but doesn't hit the bottom, allowing a chocolate base to remain intact beneath the filling. As the peanut butter sits in the base, a second dose of chocolate is deposited on top. This is referred to as the capping phase. The capping head delivers another precise amount of tempered chocolate to completely enrobe the peanut butter core. This top layer seals the filling, ensuring the product is fully enclosed and protected from oxygen, moisture, and contamination. The final thickness of the cap is carefully calibrated so the chocolate shell is strong enough to hold shape, but still soft enough to bite through easily without excessive crumbling. The assembled cups, now complete with base, filling, and cap, are conveyed into a long, multi-zone cooling tunnel. These tunnels are often 20 to 30 meters in length and feature graduated temperature zones, starting at around 16 degrees Celsius and dropping to 8 to 10 degrees Celsius toward the end. The slow, controlled cooling is essential to prevent condensation or stress fractures in the chocolate. Too rapid a chill can cause bloom or cracking, while uneven cooling can result in misshapen edges or textural inconsistency. Inside the cooling tunnel, conditioned air circulates in laminar flow patterns, ensuring that every cup is exposed to identical cooling conditions. The duration of the tunnel cycle is calibrated to match line speed and product size. Larger Reese's big cups may require longer chill times compared to the classic or miniature versions. At the tunnel exit, the cups are inspected by automated vision systems that detect anomalies like off-center fillings, insufficient chocolate coverage, or edge deformation. Any defective cups are automatically diverted from the line for reprocessing. The cups that pass inspection are ready for packaging. But before that happens, there's one last critical test: weight and sealing verification. Inline check weighers use load cells to weigh each cup or group of cups to ensure they fall within designated tolerances. Simultaneously, barcode scanners and optical sensors check that each product is aligned and properly seated in its paper cup. The final stage before wrapping is an air dusting system that removes chocolate crumbs, static particles, or paper fragments from the surface to ensure a clean, polished presentation in the final package. Packaging of Reese's cups is a high-speed operation. Cups are grouped automatically into configurations appropriate for each product format: singles, twin packs, snack-size multi-packs, or seasonal variations. Each group is loaded into a continuous film wrapping machine, which pulls branded plastic film from a roll, wraps it around the cups, seals it with a heated crimper, and cuts it into individual packages. The film is pre-printed with product information, UPC codes, and freshness dates that were applied earlier by industrial flexographic printers. Once wrapped, the products pass through another metal detector or X-ray system to detect any foreign contamination that may have occurred during packaging, a standard in modern food manufacturing. Any anomaly results in immediate ejection and shutdown of the machine until the issue is resolved. The acceptable product continues to cartoning lines, where it is packed into retail-ready boxes, display trays, or bulk shipping cases depending on the destination. Finished product cartons are coded, palletized by robotic stackers, and shrink-wrapped for transport. Each pallet is labeled with a unique tracking number that links it to its production batch, shift number, ingredient lot codes, and quality control logs. This traceability allows for quick response in case of any issues in the supply chain. Every Reese's Peanut Butter Cup batch is subject to a comprehensive quality assurance protocol from start to finish. While visual inspection, weight checking, and foreign material detection handle surface-level defects, deeper analytical testing is performed regularly throughout production. Factory labs adjacent to the production floor run hourly tests on product samples pulled from the line. These tests measure water activity, pH levels in the peanut filling, chocolate temper index, fat content, and emulsifier concentration. Advanced equipment like near-infrared spectrometers and gas chromatographs are used to validate these metrics with precision. In addition to instrument-based testing, trained sensory panels perform blind evaluations of finished product samples. These panels, often composed of factory employees specially trained in flavor and texture recognition, assess everything from peanut aroma intensity to shell firmness, sugar balance, and mouthfeel contrast between chocolate and filling. Feedback from these panels is compared to golden standard benchmarks. Reference Reese's cups produced under ideal conditions that are stored in temperature and humidity-controlled archives. These control cups are regularly reviewed to ensure no drift in product quality over time. Allergen control is one of the most sophisticated systems running silently beneath the surface of Reese's production. Since peanuts and dairy are both major allergens, Hershey facilities that manufacture Reese's operate under strict protocols to prevent cross-contamination. Separate ingredient receiving docks, isolated storage silos, color-coded tool systems, and dedicated air handling zones are used to segregate peanut-related materials from other production lines within the same facility. Sanitation crews follow clean-in-place procedures using food-safe alkaline and acid-based cleaners to remove all traces of allergens between product changeovers. Swab testing for peanut protein residue is conducted on all contact surfaces before production resumes. Hershey also enforces supplier controls. All incoming peanut shipments are tested for aflatoxins, a class of toxic compounds produced by certain molds that can occur in improperly stored peanuts. Only peanuts that pass stringent safety thresholds are accepted, and each delivery is logged and tracked using batch codes that link to the final product's traceability system. This digital record keeping allows Hershey to track every ingredient back to its source farm and forward through every unit sold. But Reese's isn't just a singular product anymore. Over the years, the brand has expanded into dozens of variations: white chocolate cups, dark chocolate, big cups, miniatures, stuffed versions with pretzels, potato chips, Reese's Pieces, or caramel. Each variant requires its own unique processing conditions and introduces new complexity to the factory system. Let's take the white chocolate Reese's as an example. This variation uses a cocoa butter-based confectionery coating rather than traditional milk chocolate. It must be handled in separate melters and tempering systems due to its sensitivity to high heat and faster tendency to bloom. White chocolate also requires precise control of ambient light and humidity during production and packaging, as it is more susceptible to visual imperfections. On the line, switching from standard milk chocolate to white chocolate triggers a full line cleaning and recalibration of depositor and cooler settings. Flavor variants with inclusions, like Reese's with Reese's Pieces inside, add another layer of complexity. In these formats, the peanut butter filling is first blended with the inclusion, pieces, chips, or even candy bits, using slow-speed paddle mixers to avoid crushing or melting the added components. These inclusions alter the viscosity and extrusion behavior of the filling, requiring depositor nozzles to be widened and dosing pumps to be recalibrated for accurate weight control. Additionally, because candy-coated pieces can crack or leak color when exposed to oil migration from the peanut butter, the storage conditions of these fillings must be tightly managed to preserve structural integrity during molding. Even packaging formats are adapted. Big cups, which contain more filling and sometimes additional elements, require thicker paper cups and slightly wider flow wrapping machines to handle the larger size. Seasonal versions, like pumpkin-shaped Reese's for Halloween or tree-shaped cups for Christmas, require completely new mold tooling, reshaped paper cups, and different wrapping film dimensions. These seasonal SKUs are often produced in limited time production runs scheduled between mainline batches, with precise coordination between departments to minimize downtime and clean out inefficiencies. To manage this growing complexity, Hershey's manufacturing ecosystem is deeply integrated with real-time data and automation. Programmable logic controllers govern every stage of production, from peanut grinding to chocolate capping. These controllers constantly adjust conveyor speeds, depositor volumes, oven temperatures, and cooling rates to match product specifications in real time. Sensors along the line feed back information on humidity, belt tension, machine vibration, and material flow. If any parameter drifts beyond the preset tolerance window, an alert is triggered immediately and logged by the manufacturing execution system. The MES serves as the brain of the operation. It logs every batch, shift, operator, ingredient lot, and test result. It manages production schedules based on demand forecasting from Hershey's enterprise planning systems, and it ensures the right packaging, ingredients, and machines are prepared for the next product variation before the current one is even complete. The MES also interfaces with digital traceability systems, allowing Hershey to execute complete recalls if necessary, though this is extremely rare due to the redundant safety nets in place. To support sustainability goals, the factory also measures key environmental metrics. Energy usage from roasting, tempering, and cooling operations is tracked and optimized. Waste heat from roasters is sometimes redirected to preheat water for sanitation systems. Chocolate scrap from edge trimmings and overflows is collected and reworked in designated reclaim tanks. Even the cardboard used for cartons and paper used for wrapping is sourced from certified sustainable forestry programs. Water used in cooling tunnels is recirculated through industrial-grade filtration systems and UV sterilization loops, allowing for multiple reuse cycles before any disposal. Factory roofs are often equipped with solar panels, contributing to the site's renewable energy footprint. These sustainability measures not only support Hershey's corporate goals, they also help reduce operating costs and ensure compliance with international environmental standards, especially for exports to markets with strict eco-regulations. Finally, at the distribution level, finished pallets of Reese's are scanned, shrink-wrapped, and entered into a dynamic warehousing system. Pallet storage is optimized by weight, sell-by date, and destination zone. Reese's products are shipped in refrigerated trucks when needed, although standard varieties are stable at room temperature due to their low water activity and solid fat matrix. Shipments are tracked via GPS and load sensors to ensure they remain within safe handling conditions throughout transit. So when you open a Reese's peanut butter cup and experience the snap of chocolate, the softness of the peanut filling, and the perfectly even texture from edge to edge, what you're actually tasting is the output of a meticulously engineered, continuously monitored, and relentlessly optimized factory system. Behind every wrapper is a chain of roasting drums, tempering tanks, vibration tables, chilled tunnels, microlab samplers, PLCs, conveyors, AI sensors, and hundreds of trained hands working in quiet unison to make every bite familiar, reliable, and timeless. As Reese's peanut butter cups leave the controlled environment of production and are loaded onto outbound trucks, the story doesn't end with the last machine seal or pallet scan. In fact, one of the most underappreciated aspects of the manufacturing system lies in how Reese's maintains product integrity far beyond the factory walls. The journey from factory to store shelf, and ultimately to the consumer's hand, is an extension of the manufacturing process itself. For a product like Reese's, where texture, flavor, and structure are so carefully engineered, maintaining those qualities through shipping, storage, and retail presentation is non-negotiable. Temperature control plays a key role in this extended quality assurance chain. While Reese's peanut butter cups are classified as shelf-stable and do not require refrigeration, they are extremely sensitive to heat and humidity. Elevated temperatures can cause the chocolate to melt or bloom, a condition where cocoa butter rises to the surface and creates a whitish-grey coating. Though harmless, bloom gives the appearance of staleness or spoilage and is unacceptable in any retail-facing product. To prevent this, shipping containers and trucks are monitored using digital temperature loggers and GPS trackers. These devices not only ensure compliance with storage requirements, but also provide real-time alerts if conditions fall outside predefined thresholds. Warehousing and retail logistics are optimized with similar care. Distribution centers receiving Reese's shipments are instructed to rotate inventory on a strict first-in, first-out system to preserve freshness. Shelving time is tracked down to the day, with expiration dates digitally logged and printed clearly on all packaging. Retailers are often supplied with merchandising guidelines from Hershey's sales and operations teams, advising on optimal product placement to avoid heat sources and maintain visibility in high-traffic zones. This ensures not just product survival, but also consumer engagement. Meanwhile, Hershey's central data systems stay connected to the broader supply chain. Sales velocities from thousands of retail points are monitored using automated inventory systems that integrate with distribution algorithms. If Reese's products are selling faster than expected in one region, perhaps due to a seasonal promotion or viral social media trend, production forecasts and shipment routes are adjusted in near real time to prevent outages. Conversely, if stock is underperforming, the system can slow production or reroute product to a region with higher demand. But what truly sets Reese's apart in this final segment of its manufacturing cycle is its flexibility for innovation and customization, especially on a global scale. Reese's peanut butter cups aren't manufactured identically across every country. Although the core elements remain the same, formulations may be slightly adjusted to meet regional preferences, regulatory standards, or ingredient availability. For example, Reese's produced for the European market may contain non-GMO ingredients or use different emulsifiers to comply with EU food safety regulations. Sugar content, fat ratios, and even packaging inks are tailored to local markets, and each international facility must pass regional audits to ensure compliance with both Hershey's standards and those of the target nation. Seasonal and limited edition Reese's lines introduce another layer of production complexity that extends into post-factory strategy. Every year, variations such as pumpkin-shaped Reese's in October, tree-shaped ones in December, and heart-shaped versions for Valentine's Day hit the shelves. These products require not only physical retooling, custom molds, unique wrappers, modified flow wrappers, but also adjusted production timelines to accommodate pre-holiday distribution. Most holiday variants are produced months in advance to ensure they hit retail shelves in time for the season, but remain fresh through the actual holiday window. To ensure holiday versions meet the same performance standards as core SKUs, Hershey uses accelerated shelf life testing. In these tests, products are stored at elevated temperatures and humidity for a condensed time frame to simulate long-term storage. The samples are then analyzed for fat migration, filling breakdown, wrapper integrity, and flavor degradation. Only those variants that meet Reese's strict internal benchmarks for shelf life, texture stability, and visual appearance are approved for full-scale seasonal release. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers such as polyisobutylene and polyvinyl acetate provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes like paraffin and microcrystalline waxes are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble-forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are, is specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum base formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer, this time designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The re-softened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial-scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise. Too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, dent, and humidity-controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, the film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large, stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed check weighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, the products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering.